So in this video, we're going to talk about radicals. Did you know that radicals are actually the opposite of exponents? So an exponent, I'm sure you've seen this before, 3 squared. The 2 will be the exponent. And 3 squared is the same as 3 times 3. And when we simplify that out, we get 9. Well, a radical actually undoes or reverses this squaring. Let me show you what it looks like. So a radical looks like this, and it undoes the corresponding exponent of a number. So let's say we have x to the n. This number on the outside undoes the exponent on the inside, and this number on the outside is called an index. So actually, you can cancel it out and end up with x, with just x. The radical tells you to find the perfect square, perfect cube, perfect quad, or perfect whatever under the radical, depending on the value of the index, the small number, which we have as n. And it tells you to root it out. Root out the number. So that's what we did. Let me give you an example. We have 27. And we're finding the cubed root of 27. So this number would be the index. The number under the radical would be the radicand. This symbol is the radical symbol. And this whole thing is called the radical. Cool? Okay. So in an equation, you can directly reverse squaring, cubing, or powering a number by placing it under the radical, like we just talked about. You want to do that along with the other side of the equation to balance it out. And the index has to match the power or the exponent. So let's look again at 3 squared and set it equal to x squared. If we say, in order for us to figure out what x is, we have to take the square root because the exponent is a 2. So we want to use a square root use a radical that has the index of 2 also. And if ever you see an index or you don't see an index, like it's just the square root of x, you can always assume that the index is 2. So what we do to one side, we have to do to the other. So I'm just going to write the 2 there simply because it'll give us a visual of what should be there and what we're doing as far as canceling out. So we have square root of 3 squared. Like I showed you before, this square root cancels out the exponent, and we can drop out the 3. And this square root cancels out the second exponent, and we can drop out the x. And so our answer is 3 equals x, or x equals 3. Same thing. So that shows you what a square root can do. Let us start solving some square root expressions. So you may wonder, how do you take a square root? Like, how do you take a square root of a number? So say we have square root of 4, okay? Remember that little 2 is here, but it's invisible because we're able to call this square root. And that's how you usually see it, as invisible. To square root means to root out the number that is squared. You can find this out by dividing the radicand down to all primes using a factor tree. Sometimes you will only have perfect squares under the radical as the radicand. So we have a number under the radical symbol, and we want to break it down to primes. 4 is not a prime, which means that we can break it down to primes that it is, or that make up 4. So the numbers 2 times 2 do equal 4. Also, 2 times 2 would make 4 a perfect square. So what we can do is rewrite this as the square root of 2 times 2, then the square root of 2 squared, and then we can do what we just did with 3 and x by seeing that this index matches the exponent and just crossing them out and leaving ourselves with the 2 as the answer. Here's another example. We do square root of 16. With square root of 16, we can break the number down to primes because 16 is not prime. If we break it down to 4 times 4, 4 and 4 are not primes. But if we break our 4's down, we do get primes. However, it is not necessary to break our 4's down to prime numbers, the 2's, because 4 times 4 shows that 16 is a perfect square, and we can rewrite it as 4 times 4, square root of 4 squared, and then cancel out those 2's, and we're just left with 4. To cube root means that we have to root out the number that is cubed. You can find this by dividing the radicand down to all primes if you need to, using a factor tree, and sometimes you will get a perfect cube, which will be 8, 27, 64, numbers like that, which you can find on the perfect squares and perfect cube list in my Algebra's Top 7 course. So let's look at an example. We have the cube root of 8. So let's see if we break it down to primes, what's going to happen. We know 8 divided by 2 is 4. Well, 2 is a prime, but 4 is not. Remember, we want to get 3 of the same number this time under the radical because the index is 3. So 2 is good, but let's break down 4 again. That would be 2 times 2. Now I see that we have 3 of the same number. We can rewrite this same expression as 2 to the third power because that's what 2 times 2 times 2 is. And then we can cross these 3's out and just we're left with 2. Here's another one. Cube root of 27. Once again, let's break it down. We want to find 3 of the same number. So we know 27 divided by 3 is 9. 3 is prime, 9 is not. And we know that 3 times 3 is 9. And we have our group of 3 of the same number. So we can rewrite this as a cube root of 3 cubed. Cross out the 3's. We're just left with 3. There's your answer. So the reason why we were able to get just straight out whole numbers was because the numbers under our radicals were perfect cubes and perfect squares. So I want you to try some of the examples, some of the exercises that I have laid out for you in the course on the radicals section, and then go ahead and enter your answers into the knowledge check. If you need more of a in-depth review of radicals, I am creating a course where you'll be able to learn all the rules, learn when there are variables under the radical, so that'll help you to get a better understanding of how to manipulate radicals and what's under them.